I have a proton. I have an electron. Pwah, I have atomic orbitals. Atomic orbitals come in all kinds of fun, balloon-like shapes and are a pretty important tool for quantum chemistry. Here is a list of 2D projections of the first few atomic orbitals of a hydrogen-like atom. That is, of course, an electron sitting in the field of a point charge. The brightness of a pixel corresponds to how likely you are to encounter the electron at that position. Find your nearest physicist and ask him to solve the time-independent Schrödinger equation for that system, and we should hopefully plot something similar. Each atomic orbital is characterized by 3 special numbers, the so-called quantum numbers of that state. For this video though, we only need to know that n is the energy quantum number, indicating how much energy the state possesses, and the other 2 quantum numbers are related to the angular momentum. And instead of numbers, we use funny letters like S, P, D and so on to describe the value of the angular momentum. This is due to historical reasons, and also not so relevant for us right now. If we now turn our attention back to the physics, we solve the quantum problem of the electron around a positive charge quite quickly. Let's ask our physicist friend to do the same now for the next simplest molecule, the hydrogen molecule. It shouldn't be that much harder, right? Well, it is still technically solvable using numerical methods, but we can't really write down a functional form for the solution. So I think it is time to get out some approximations and hopefully obtain a scalable, albeit approximate method, since we are ambitioned and we do not want to stop at H2. It's already done. It turns out it took less than 3 years shortly after Schrödinger dropped his equation. Very nice. The Hartree-Fock method lets us find molecular orbitals using some simplifications. Since this method is not the focus of this video, I won't really tell you anything about it, other than that we need to calculate lots and lots of different integrals between atomic orbitals and sometimes with operators acting on these orbitals. So, let's look at the most relevant kinds of integrals. The simplest is the overlap integral between 2 functions phi a and phi b. We represent these integrals using these brackets, which is customary from quantum mechanics. This notation just represents the integral of the product of these 2 functions over the entire space. Next up is the so-called kinetic energy integral, which is almost the same as the overlap integral, but we act with a Laplacian on the second function. Then there is the Coulomb integral, which gives us the energy between a delocalized particle, like for example the electron, and a point charge, which we assume all nuclei to be. Finally, there is the electron repulsion integral, which gives us the energy between 2 electrons, so we need to integrate twice over space. As you can see, some of these integrals can be quite involved. It would be quite disastrous for performance if we had to numerically calculate these integrals, so we need to find some more clever way to find their values. The proper atomic orbitals that we get from the solution of the Schrödinger equation has a principally exponential fall-off and looks like e to the minus r. If you tried to solve the integrals from before with this kind of function, you would quickly see that there is no smart way about it. But what if we approximated the true atomic orbitals with a Gaussian? Or, if you prefer some more accuracy, we can approximate each atomic orbital by a sum of Gaussians. Since integrals are linear, this just means that we need to do more Gaussian integrals, but maybe that trade-off is worth the additional effort. As you probably already have guessed, using Gaussians is a viable way forward. So I want to take a moment to discuss the basic properties. Gaussians have an amplitude. This is not so important for our discussion, but that amplitude is usually set by normalizing the overlap of an atomic orbital with itself. What is more interesting is the coefficient in the exponent, which we will call by the Greek letter zeta. The larger zeta is, the more localized the Gaussian is. Finally, there is an offset, which determines where the center or the maximum of the Gaussian is located. We can use it to move the Gaussians to the atomic nuclei. In general, our Gaussians are three-dimensional. They may also be multiplied by any power of the x, y and z coordinate in order to mimic atomic orbitals with higher angular momentum. In this context, the powers I, j and k are therefore loosely referred to as the angular momentum quantum numbers. In the shorthand notation that I want to introduce, they become the indices of the Gaussian G. The three-dimensional Gaussians factorize neatly into three one-dimensional Gaussians centered along the Cartesian axis at the points ax, ay and az, where A is just a three-dimensional point. The coordinates xa, ya and za are just the x, y and z coordinates shifted to the point A. For now, we will focus on these one-dimensional Gaussians. The first question we should ponder is what happens when you differentiate the Gaussian with respect to the offset coordinate. Can we maybe write the derivative in terms of the Gaussian functions? After some quick maths, the answer seems to be yes. We can write this differentiated Gaussian as a sum of Gaussian of higher angular momentum and a Gaussian of lower angular momentum, which is quite neat. To find the answer for higher derivatives, we just apply the derivative multiple times. For my shorthand notation, the order of the derivative will be the superscript of the Gaussian G. We now have our first recursion relation, allowing us to trade the order of the derivative with the angular momentum of our Gaussians. It is not obvious yet how this is helpful, but it sure is nice to know. Another trivial relation is that multiplying by the coordinate increases the angular momentum quantum number of the Gaussian. Our Gaussians are pretty nice to work with when all we want to do is multiply them by coordinates. While we found a formula for differentiation, it is a bit complicated. Maybe we can define another type of Gaussian that works trivially with differentiation? Of course we can. These Gaussians are called Hermite Gaussians, and we will get to why in a bit. Instead of being generated by multiplication with the coordinates, these are generated by repeated differentiation along the Cartesian coordinates. We will denote them using the symbol lambda in the following. We know from their definition that differentiation acts trivially on the Hermite Gaussians, meaning that the quantum number is just incremented by the order of the derivative we apply. We would, however, like to get some deeper insight and see how Hermite Gaussians of different quantum numbers are related. So we write out explicitly the differentiation of lambda 0. Now we just need to swap xp with the differentiation. You need to be a bit careful, but it's definitely possible. What we have so far is a recursion relation for differentiation, but we don't really need that. Let's instead bring the product with xp to the left. This way we obtained a recursion relation for what happens when you multiply a Hermite Gaussian function by the coordinate, expressed in Hermite Gaussians of different quantum numbers. Doesn't this look very similar to the relation for differentiation of normal Gaussians? As a reminder, here's what we derived so far. There are normal Gaussians and Hermite Gaussians. Higher angular momenta can be achieved by multiplying normal Gaussian with the Cartesian coordinates, or taking the derivative of the Hermite Gaussians with respect to the coordinates. Multiplying the normal Gaussian by a coordinate is trivial to express as another normal Gaussian. By multiplying a Hermite Gaussian by a coordinate yields a relation which is a bit more complicated. On the other hand, derivatives of coordinates are trivial for Hermite Gaussians, while it yields another recursion relation for normal Gaussians, which looks quite similar to the relation for Hermite Gaussians. We already did a lot of algebraic preparation, but it is time now to look at what the most basic Hermite Gaussian integral actually evaluates to. We can just plug in the definition and see where that takes us. We can swap integral and derivatives when Leibniz says so, and Leibniz says it's cool in this case. The integral we are left with is just a standard Gaussian integral, which is well known. Since the integral evaluates to a constant, the derivative is always 0. We can also have no derivative when the entire thing just evaluates to the Gaussian integral. This is encoded by the usage of the Kronecker delta. Another thing that might be bothering us is that it's not so easy to write the Hermite Gaussians as concrete, explicit functions of x. I mean, sure, it is the tth derivative of that Gaussian, but what actually is the resulting polynomial as a function of x? We will now try to see if we can find that polynomial h. Don't mind the very specific scaling we introduced on the amplitude and coordinate, these were just chosen by the power of hindsight. To start with, we use the recursion relation for Hermite Gaussians and plug in our new functional form. The exponential terms cancel, as does p to the power of t half. Some more simplification and rearranging. This equation looks very much like Hermite's differential equation. We can also observe that the 0th order polynomial is just the constant number 1. This brings us to the conclusion that the polynomials in the Hermite Gaussian functions are actually Hermite polynomials, which explains the name. We are now very well equipped to start looking at the actual integrals that we need for quantum chemistry. Let us now look at what happens when we multiply two arbitrary Gaussians. Interesting, right? It seems as though the resulting function is again a Gaussian. The question is this always the case, or did we just get lucky somehow? It turns out that the product of two Gaussians is indeed always another Gaussian. Proof not included in this video. Even better than that, we can give an explicit formula. On first glance, it just looks like another product of two Gaussians. But notice that the first term is just a constant in x. We will call this KAB, as in constant of the product between Gaussians A and B. We also introduced some other variables to neatly write down the product. If you are interested, you can read all of this. Since we now know that a Gaussian product is always a Gaussian, we can write the product of our Gaussian basis function as some constant times the exponential term. If there are any polynomial prefactors, they just get multiplied together. We will call this product of Gaussians, or the more common name, the overlap distribution, by the symbol omega. And to remove clutter, I won't explicitly write the arguments of the functions. If we look at the overlap distribution, we will notice that there is a polynomial in front of the exponential term. If you know a thing or two about Hermite polynomials, you might see where this is going. And for those of you who don't, I will tell you the single most important fact about Hermite polynomials for our investigation. You can write any polynomial as a sum of Hermite polynomials. In our case, it doesn't really matter how you would get the expansion coefficients. That whole topic is a rabbit hole you have to explore on your own. For us, it only matters that you can do it, or in other words, that this decomposition always exists. Putting what I just said into a formula looks like this, where p is any polynomial and e are the expansion coefficients. I is the order of the polynomial and t the order of our Hermite polynomials. I want to repeat our observation from before. The overlap distribution looks like a polynomial of degree I plus j times an exponential function, which means that we can decompose the polynomial part into a sum of Hermite polynomials. We index the expansion coefficients separately in I and j, which is not strictly necessary here because in this integral only the sum of I and j matters. However, it's good form for when we have integrals that are asymmetric in I and j, for example because the derivative only acts on the functions to the right. We can move the constants over and see that the rightmost terms kind of resemble our Hermite Gaussians. Any mismatch in prefactors we will just absorb into the expansion coefficients, so that we can replace all these terms with the Hermite Gaussians that we know and love. Now we just need to figure out how to actually calculate the expansion coefficients. Our method of choice is again induction. We will try to see how the case with I plus 1 relates to the case with I. A similar approach can be taken with j, which I will skip. Let's see. Omega I plus 1 j is just omega ij multiplied with xa, the x-coordinate associated with Gaussian A. This expression would probably be more useful if it was in terms of xp, the x-coordinates associated with the product Gaussian. Luckily, we know how these things are related thanks to the Gaussian product theorem. Using the relations from the theorem and some clever ways to write ones and zeros, we can transform the expression in terms of product Gaussian variables. I encourage you to work through the details yourself, or you can just believe me. Now we know how the omegas of different quantum numbers relate to each other. It should be easy now to go from there to relations between the Hermite expansion coefficients. The term multiplied with xp is a little bit more troublesome, so let's look at that in isolation. We need to do some simplifications and clever reindexing of the sum, but end up with a nice expression that looks usable. Now we bring it all together. The left hand side also gets expanded, and when we say that the two sums equal if and only if all sum terms with the same t fulfill the equation. From this we can get a general recursion relation for the coefficients. We can use this to lower the quantum number I. Like I said before, we could play the same game with the other quantum number and would get a very similar relation, lowering j instead of I. And just from looking at the Gaussian product theorem and our definitions, we can see that the expansion coefficients with the lowest quantum numbers is KAB. We will now look at the big boy quantum chemistry integrals. First up are the multipole integrals, which are generalized overlap integrals. These include 3 dimensions. The Gaussians are 3-dimensional and the polynomial in the center is as well, while the integral still evaluates to a single number. Luckily, this is not really a problem, since the integral immediately decomposes into 3 one-dimensional integrals. Looking at one of these integrals, they look already quite familiar, but we need to be careful. The operator in the middle is a power of xc, not of xp. xc is an arbitrarily shifted coordinate system, so we cannot assume it coincides with our very convenient product Gaussian coordinates. Plugging in our definitions reveals that we need to solve yet another integral. This is the last one, I promise. Let's call the resulting integral m with the appropriate indices. By now, you know the drill. We use induction and look first at the base case e equals 0. We already know the value of the basic Hermite Gaussian integral, so that was easy. What about the case e plus 1? xc times Hermite Gaussian is kind of hard to evaluate, so let's try to rewrite that product into something that doesn't have that x dependence. Well, this term still depends on x. What I meant is that the dependence on x is now packaged solely into Hermite Gaussians, which we understand a lot better. The resulting integrals look basically like our induction case e. So this finally gives us another recursion relation, this time for the integrals we need for the multipole integrals. A quick note on these integrals. If we look a bit closer, we can also figure out when an integral evaluates to 0 just by looking at the indices e and t, saving us a few recursion steps if we implement this in code later. The fruit of our labor is that we can write a multipole integral just in terms of coefficients and integrals that we can calculate very quickly and exactly using recursion relations, with the added bonus that the base cases of these relations are also relatively simple numbers. We can now look at the so-called momentum integrals, which have a different central operator. Instead of multiplying by a power of each coordinate, in the momentum integrals we apply the derivatives along each axis repeatedly. Since this decomposes like the multipole integrals, it is enough to look at a one-dimensional momentum integral. By now, our induction approach should be second nature to you. In the case of a 0th power derivative, the momentum integral just evaluates to a multipole integral. To figure out the q plus 1th derivative integral, we apply the first derivative once and use one of our recursion relations to write everything in terms of Gaussian functions. This results in a recursion relation for momentum integrals, which we can apply easily. To finish this video, I want to show you some commonly used integrals and how we can write them in terms of the multipole and momentum integrals that we now can evaluate swiftly. First up is the linear momentum. Second is the kinetic energy. And finally, the angular momentum. Admittedly, I have never used this one, I think, but I was told that it is useful and the multiple terms make it a good educational combination of basic operators. I am aware this video is quite dense and fast moving. Since I am yelling into the void, I just made this video as a note to myself. For others and me in the future, I just want to quickly recap the most important things that we derived in this video. We started with the observation that proper atomic orbitals have an exponential shape. Since integrals involving these are not efficiently calculable, we approximate each orbital with a sum of Gaussians. Finding the right combination of Gaussians is an art in and of itself, as there are many basis sets with slightly different properties. We derived an expression for the overlap integrals with the help of Hermite Gaussians. The value is given by a sum over expansion coefficients and a helper integral. Both the coefficients and the helper integrals are defined recursively, allowing rapid computation of their values. We also know how to calculate the momentum integrals. They follow a straightforward recursion relation, with the base case being a simple overlap integral. We skipped some other very important integrals, which all have to do with electrostatic forces. Due to the integrals were having singularities, we cannot simplify everything quite as nicely as what I have shown you here. I want to work on a second part and then show you a reference implementation of the code calculating also these integrals. But I think for this video you made good progress and you already learned the gist of the methods for fast evaluation of Gaussian integrals. So see you in another video. Bye!